Welcome to Gotta Cache Them All, Bending the Rules of Web Cache Exploitation. This is the agenda for today. First, I'm going to briefly explain how a web cache works. Next, I'm going to show how we can abuse different URL parsing discrepancies between an HTTP server and a cache proxy in order to steal some sensitive information from a victim and obtain arbitrary web cache deception. Then I'm going to show how we can use similar techniques in order to modify the cache key of a stored resource and obtain arbitrary web cache poisoning. And then I'm going to combine both techniques in order to store any resource we want with any key we want and obtain a full defacement of our website. Finally, I'm going to show some defenses that can be used to protect against these attacks and the takeaways of the session. So before I dive into the talk, I have to say that most of these examples that you are going to see are based on CDNs like Cloudflare, CloudFront, or Akamai. But all of these attacks can be used and applied in any kind of web cache, so even those that are included in the same HTTP server. So whenever we send a request to a website that is using a web cache, the first thing that is going to happen is that the request is going to be handled by that web cache proxy, and the idea is that he will try to resolve the request by generating a response that is already stored. So to do that, it's going to calculate the key of the request, and the key is basically an identifier that just says which is the resource that is being requested. So usually it's a string containing the URL and the host header. So the idea is that if we have two requests with different cookies or different user agents, we will still be requesting the same resource, and therefore the response should be the same if the resource is static. So after calculating this key, the cache proxy is going to look at the table, at the cache table, and if there's now no resource ready for that request, then it's going to forward it to the origin server. Now the origin server is going to parse the URL to obtain the path and map the endpoint that should resolve the request. Sometimes it's a dynamic endpoint, and sometimes it's just a static file that is going to be served. So when the origin server sends the response back to the cache proxy, this response is going to be evaluated as well as the request using some rules that will tell the cache proxy if this resource is static or not, and if it should be stored or not. And in the response, it's going to observe the cache control header, which is going to tell some directives that can tell if the resource is static and should be stored, and this is created by the origin server. But also, it could look at some other things in the request, such as the URL, and it can compare it with some strings, and depending on the behavior of that evaluation, it will be able to know if the response is static or not. One really common rule that is applied in many CDNs by default is the static extension rule, that in this slide you can see the static extensions that are defined in Cloudflare by default. And the idea is that if the path of the request ends with any of these extensions, then the request or the response should be stored in the cache. So in this case, as you can see, the request is to styles.css, and as it ends with a static extension, the cache proxy is going to decide that it should be storing this response. And it will use the key that was calculated in the first step to store this, so that whenever a client, maybe the same or other client, sends a request looking for the same resource, the cache proxy is going to calculate the key, is going to find a response ready for that key, and is going to deliver it back to the client. So all these steps involve parsing the URL and obtaining the path. And this can lead to different kind of unexpected behaviors, because if the parser from the origin server and from the front-end server, which is the cache proxy, are different, then the path could be interpreted differently. This is what happens when we try to attack an application using a cache proxy with an attack that was presented a few years ago by Omar Gill in Black Hat 2017. And what he realized was that some backend servers were using a special mapping where the only thing that is compared is the prefix of the URL, and then the rest is considered path, is considered parameters. So these are called path parameters. So if we send a request to my account /param1/param2, only the first part is going to be used to look for the endpoint, so my account, and the response is going to contain, in this case, a lot of information from the victim, like the email and the credit card. That's the response that we want to steal. So to do that, we are going to send a malicious link to a victim. This is what Omar Gill discovered. And we were going to use the path that is my account, but also a parameter that is called a.js. So when this is forwarded to the origin server using the cookies of the victim, the origin server is just going to look for the first part, which is my account, and the rest is going to be considered as a parameter, so it will return the response containing all the secret information. Now, as the cache proxy is not aware of this special mapping, it's just going to think that the end of the path is still part of the path, so it's going to think that this contains a static extension, and therefore the response should be stored in the cache. And now, if an attacker sends the same request without any cookie or without anything, because it's not part of the key, the cache proxy is going to find that there's a response ready for that, and it's going to send back the victim's response containing all the secret information, and we will be able to obtain that data. But the problem with this attack is that if there's no special mapping, then we cannot create any web cache deception attack. And also, if the path parameters have any special meaning, like we cannot send a.js because it's going to be interpreted in the origin server, then this attack is again going to fail. So what I decided to do is to look for other kind of path confusion techniques that could be applied to make these discrepancies and eventually be able to store a dynamic response. And to do so, I started looking at how the path is obtained from a URL. And this is done by using what the RFC calls path delimiters. So basically, these delimiters are characters, reserved characters, that will tell where each of the elements of the URL starts and ends. So a URL contains different elements, such as the scheme, the credentials, the host, path, query, and fragment. But to split them, the RFC says that you can use these kind of delimiters. The problem is that the RFC says that they may or may not be used as delimiters, so it's entirely depending on the implementation, and that's where the problems begin. Because if we can find a delimiter that is being used at the origin server but not at the front-end server, then we can actually send the same request, which is my account. Instead of /, we would send the delimiter, in this case, a $, and a.js. The origin server is going to use the delimiter, and it's going to say that the path is actually my account. But as the front-end is not using the delimiter, then it's going to think that the entire URL is part of the path, and it's going to think that this is a static file because of the static extension, and it's going to store the response. And what's really cool about this attack is that we can use it with any kind of resource, so we don't really depend on any mapping, and we can steal any kind of thing. So not only my account, we could steal other responses like secret or anything we want. So let's see which delimiters we can find in the wild to use this and to exploit an origin server that is using them. The first one is one that is really well known by a lot of people, which is the Spring semicolon. In Spring, we can define matrix variables, and we can include them in the path. So if we send something like my account, semicolon, a.js, well, Spring is going to think that this is just my account, and a.js is a path parameter, or actually a matrix variable. Then in Rails, this is a really cool one because I never saw anyone using it. In Rails, we can use the dot as a delimiter. And this is because Rails, when we create a view in Rails and an endpoint that answers for that view, the expected behavior for Rails is that when we send something like my account, it's just going to look for the my account HTML view. Okay? However, if we send my account.css, well, Rails is going to still think that this is a request to my account, and it's going to try to load the CSS version of the view. So it's going to look for my account.css, and if there's no view for that, then it's just going to return a 406 error, which is not really useful for us. However, if we send something like my account.aaa, well, Rails doesn't think that this is a valid extension, and therefore it's going to use the default view, which is HTML, and it's just going to send us back the response. These are the static extensions that we saw that are accepted by Cloudflare. And also, in green, you can see the extensions that are known by Rails. So if we send something like my account.png or JS or CSS, then Rails is going to look for that view. And if it's not there, then it's going to just return an error. But these are all the other extensions that are not known by Rails and that are going to be responded with the HTML view. So if we send something like my account.ico, which is going to be stored in the cache because it's a static extension, then Rails is just going to load the HTML view, and we will be able to use it as a delimiter to hijack any sensitive response. There are also other delimiters that are not in frameworks, but in HTTP servers, such as the encoded null byte in Open Lightspeed. So if we send this null encoded byte, it's going to just behave like a question mark, and it's going to be used as a delimiter. So it's going to be interpreted as my account. The problem with this is that many CDNs will not forward the null byte, so we will need to find some that does, like Fastly or Akamai. Next, we can find another delimiter in Nginx when Nginx is actually configured to rewrite the rules, or to rewrite the path, sorry. And in this case, if we send an encoded new line, then we will be able to use it as a delimiter. And again, the behavior is going to be the same. We will be able to store anything we want using this attack. Now, all these examples work. They are just using the delimiter and the extension. When they are interpreted in the backend, they are all interpreted as my accounts. All these backends are going to respond with my account and with the sensitive information. And then they are going to be cached because of the static extension. But the problem with these kind of attacks is that there are already some CDNs like Cloudflare which created some defenses like web cache deception armor. And the idea in these cases is that the cache proxy is going to look for the extension that was set in the URL, and it's going to look for the content type in the response. And if they don't match, for instance, in this case, we have an extension CSS and a content type HTML, well, Cloudflare will know that this is an attack, and it will stop storing this response. So we can try to attack other kind of rules. As I said, we have the static extension that is almost always by default in any CDN, but there are also other rules like the static directory one. The idea in this case is that the path is only comparing the prefix of the URL, and if the URL starts with something like static or shared or anything that can be configured by the user, then this is going to be used as a static request, and it's going to be storing the response. But in this case, we will need to create a payload that, when interpreted in the front end, is interpreted as static, and in the back end as my account. And this is not really easy, because right now we think that the path is just obtained from the URL, and then it's used in the keys, the rules, and the mapping. But I forgot to say that there's one extra step, which is normalization. So path is usually normalized, and that is, first the URL is decoded using basically URL encodings. So we can send something like percentage and the hexadecimal value of each character, and then this is going to be decoded. And also in some cases, we will find that either the proxy or the backend is normalizing also the slashes and the dots. So we can send encoded slashes and encoded dots, and they will behave just as the decoded version. And also we have dot segment resolution, which is basically resolving path traversals. And that is, if we send something like hello /. world, well, the dot segment is going to remove the previous segment, which is hello, and we will be left with world. And also some parsers will decode and convert the backslashes into regular slashes, so this could be also useful in some attacks. So now that we know this, we can send a request that uses a delimiter that is going to be interpreted in the backend. So if we send something like this, the backend is going to use the $sign as a delimiter, and it's going to interpret the path as my account. But as the front end is not using the delimiter, it's just going to normalize the path. So first it's going to decode it, and then it's going to resolve the dot segment, so we will left with static WCD. So now, if there's a static path configured in the CDN, then the cache proxy is going to store this response because it starts with the static path, and therefore we will be able to access it using just static/WCD. Of course, this, as I said, this bypassed the web cache deception armor because there's no extension, and so there's nothing to compare. So we can use it in any case, even when they are protected with these kind of implementations. Now, we are going to see which kind of servers and proxies are normalizing the request, because that's what we need. So in this table, you can see that CloudFront, Azure, and Imperva, they are all normalizing the URL before using the path, and therefore they will all be used to exploit these kind of vulnerabilities when the backend is using a special delimiter. So this is the case where we combine Imperva, Azure, or CloudFront with, for example, Java and Tomcat. In this case, Java is going to use the delimiter, and it's going to interpret the path as secret. And in the case of Azure, Imperva, and CloudFront, it's just going to be normalized, and we will get the static. And again, this is going to be stored in the cache. Now we can use this with other frameworks such as Rails and Puma, and also with any application that is using a special mapping. So if we find something like I described in the beginning with the web cache deception that was discovered by Omar Gill, then we can use the same technique if this special mapping is applied. Now, I said that there is a discrepancy in normalization when the front end is normalizing and the back end is not. But what happens when the front end is not normalizing and the back end is? So this is the case for Cloudflare, Fastly, and Google Cloud Platform, and also in the back end, Nginx, OpenAI, and IIS, they are all normalizing the path. So if we send something like static slash the encoded dot segment and secret, we are sending the encoded dot segment because the browsers, the victim is going to be sending this, and we cannot send it without encodings. So this is going to be interpreted just as it is because there's no normalization in the front end, but the back end is normalizing the request, and therefore the path is going to be interpreted as secret. So the response is going to be to whatever resource we want, in this case secret, and the front end is going to think that this is a static resource because of the static path, and therefore is going to store the response. This vulnerability was found in OpenAI and allowed to extract any kind of token, API token, from any other user we want. Now, I also found that there's a normalization discrepancy between IIS and any other CDN, and that's because IIS is the only one that is normalizing backslashes. So when we send something like the request that we see in the slide, basically IIS is going to consider this as a count. However, all the CDNs that we see in the slide are all going to think that this starts with static, and therefore that this should be stored in the cache. And if there's no static directory configured by the user, then we can try to target another rule, which is the static files. So basically, in many CDNs, by default, they will be storing some files like robots.txt, sometimes favicon, sometimes index.html, and they can also be configured to store other resources. And the idea is that in this case, we need that the path is exactly the same as, in this case, robot.txt. So we can extend the same technique that I explained previously to modify the expected result in the front end and the back end. So basically, the first part of the URL is going to be used in the back end because of the delimiter, and then the last part is going to be used in the front end because of the normalization. So if we try to steal secrets, then we can use robots.txt to store this. Basically, we will send a request that is going to be interpreted as secret in the back end, and is going to be interpreted as robots.txt in the front end. So web cache deception is really good, but we need user interaction. And I wanted to find an attack that I don't require any user interaction at all. So the other way we can exploit a web cache is using web cache poisoning. And basically, in this attack, we are going to try to store a malicious response, in this case, a response that contains a script that was reflected because of the cookies. And the idea is that because the resource is being cached, because it contains the cache control header, then this is going to be poisoning the home page. However, when the client tries to access home, he will just get this stored resource, and he will be exploited with the script that was injected. But the problem is, what if we have to poison, if the response that we poison is not accessed by anyone when they navigate through the website? So let's say that the vulnerable endpoint is files, your username, and a unique identifier, then this is probably not going to be visited by any user. So in this case, we will need some user interaction, and again, this is not really useful in web cache poisoning. So what I wanted to do is to modify that key so that we can modify what is being poisoned and eventually be able to poison and affect any user navigating through the website without having to interact with them. And to do so, we will use key normalization. Basically, key normalization is using normalization to create the key. And this is by default in Imperva, Azure, and partially in Akamai. And this can also be configured in any other CDN. And the way we can detect if the key is being normalized is by sending a request to styles.css or any other resource that is cacheable. And if we observe that this is being retrieved from the cache, then we just need to modify the path so that when normalized, we again get styles.css. If we get that the same response, and the response was also obtained from the cache, so for instance, if we find that there's a xcache header with the value hit, then we will be able to use this and modify the key, as I'm going to explain later. So if we have this key normalization and we find that there's a delimiter at the back end, then we can use the delimiter to create a path that is going to be interpreted as exploit, which is the path that is getting the response with the malicious content. And then we can use normalization to modify the path that is poisoned, so we can put anything we want, and this allows us to create an arbitrary web cache poisoning attack. So I'm going to show how we can use this in Imperva, but first, let me say that even though I stated that there were 4 delimiters that are really useful and can be used in any application, there's also one extra delimiter that we weren't using in cache deception, which is the hash, and that's because the browser will not send anything after the hash. Even in some conditions, we can exploit this if the delimiter is going to be decoded, but in most cases, it's impossible to use it in web cache deception. But the thing is different for web cache poisoning because we can just open a boot session and send this directly to the website. And the interesting thing about the hash is that Imperva, for instance, Cloudflare, and Fastly, they don't consider that the hash is a delimiter, so they will just behave like it's a common character, like an ASCII value any other. And the thing is different for a backend server because Nginx, Unicorn, Puma, Rails, Flask, Laravel, and many others, they all consider the hash as a delimiter. So basically, if we send something like XSS, the hash, and then the path that is going to be normalized, what's going to happen is that the backend, any of the ones I mentioned, is going to convert this to XSS, and it's going to generate the payload, which contains the malicious response that the attacker wants to use to poison another resource. Now, Imperva is not going to use the hash as a delimiter, and therefore it's going to just normalize the path, and then we will get home, and so the home page is going to be poisoned. Now, when an attacker sends a request to home, he will be able to when the user is visiting home, he will get the poisoned response, and he will be affected by this. And this vulnerability was found in Bitstamp, MasterCard, and T-Mobile, and many other bug bounty programs. And I invite you to look for all of them because this behavior is still observed in Imperva and in many other CDNs. And we can use the same technique with other delimiters, like the semicolon for Java. And in this case, we could also use Azure, because in this case, Azure is normalizing the key. So if we have Azure, Imperva, and any other backend using Java or Tomcat, then we will have the same effect. And the same happens with Rails, with Nginx, and with any backend that is using this special mapping to find the endpoint that should handle the request. So let me show how we can use Azure. Now, in this case, we are going to use the hash as a delimiter in the front end. And this is the only delimiter I found that affects a front end and not a back end. So that's why the hash is also really interesting for me. And in this case, Azure considers the hash as a delimiter, but this is not true for OpenLight, for Django, or for Express. So if we have a delimiter at the front end, and it could be other delimiters also, not only the hash, but in this case, I found that it was affecting Azure in this way. So if we are using a delimiter in the front end, what's going to happen is that the path that is going to be obtained from this URL is just going to be home because of the delimiter. And then if the backend is not using the delimiter, it's going to just normalize the URL, and we will be left with exploit. So again, we will be able to poison the home page with any exploit or any response we want. This was found again in OpenAI because they were using Azure, and I think it was Python in the backend. So what if we don't have any payload to use as an exploit or to store for the poison endpoint? So in this case, let's say we don't have any XSS or anything that we can use to reflect and to affect a user. Well, pretty easy. We can just choose any static resource like styles.css, and we can start poisoning every single endpoint with this response. So that when a client tries to access home or my account or any other endpoint, he will just receive the CSS, and this will be eventually leading to denial of service. So now I'm going to show how we can combine both techniques in order to store any payload we want and to exploit any application by modifying the behavior of like the home page or any page that is going to be visited by a user. To do so, first we need to identify a malicious response. So in this case, the response is basically evil.com. The response is the one obtained from logout. So in this case, we have an open redirect. And it's pretty easy because in this case, we are including an X-forwarded host header. And this header is going to be used for creating the relocation header in the response. And so we have an open redirect. And as you can see, there's no cache control header, so this shouldn't be really exploitable. We can't use it in anything. So right now we have the payload that we want to use to store and to modify the behavior of the application. Now, what we are going to use is we are going to look for a resource that we want to poison. So we want to modify the behavior of another resource. And in this case, I'm going to use main.js. And that's because when the home page is loaded, it's going to import this main.js script. And so we want to modify what is being returned for that resource. And the idea is we're going to try to put an open redirect in the place of the main.js so that when the browser loads the home page, it will look for the main.js script, and this will return an open redirect, which can be used to redirect the victim browser to a malicious server, and this server is going to return a malicious JavaScript that can be used to modify the behavior of the browser. And I'm going to show a demo using Imperva and Nginx. And the idea, again, is to include a URL that starts with the malicious endpoint, in this case, logout. This will include the X-forwarded host header to generate a malicious open redirect response. Now, as the cache proxy, in this case Imperva, is normalizing the path, it will think that this response should be stored in main.js. And as the main.js has a static extension, it will think that this is a static resource and it will be stored in that place. Now, when the user sends a request to home, this request is going to be forwarded to Nginx, and Nginx is going to return the home page, which tells the browser that it should load the main.js script. So the victim's browser is going to look for that, and it's going to send a request to main.js. Now, Imperva has a response for main.js, so it's going to send a response, which is an open redirect. Now, the victim's browser is going to follow this redirect, and it's going to go to the evil.com server, which is controlled by the attacker. The attacker is going to return a JavaScript that is going to be used in the home page. And so we will be able to create any JavaScript we want and inject it in the home page, and in any page that is using actually main.js, which usually is a lot of pages. And if we have something like a content security policy that is not allowing us to load a script from another place, usually we won't find a CSP policy that prevents from loading CSS. So we could also use this to modify the behavior of a CSS and have a CSS exfiltration. If you watch yesterday's talk from Gareth, then you know that this can be used to extract anything we want. So I'm going to show the demo. So this is the web page that we are going to attack. It's using Imperva. It's using Imperva right now, so hopefully they didn't fix it. As you can see, when we load the home page, nothing happens. So if we send a request to the home page, we will see that it's including this script. So that's the script we want to modify. Now, this is the actual value of the script. And as you can see, it's being cached Okay, I set it for 25 seconds, so we will be able to cache it anyways. And what we want is to modify the response of this resource with the open redirect. Now, this is the open redirect. If we send a request to it, we'll see that it's reflecting the X-forwarded host header in the location. And also, what's really interesting is that in this case, I added a cache control header, which says that this is private, no store. So it's basically the origin server is basically saying to the front end that this shouldn't be stored, and this is not a static resource. So we are doing everything right from the origin server point of view. Now, this is the malicious server, and if we send a request to login, which is the page that is going to be loaded, then we see that we have the malicious JavaScript that we want to load and we want to use to poison the victim. And finally, this is the attack. So what we are going to do is we want to create a response for logout, and we want to include the hashtag. This is because the backend is going to just use this as the path because of the hashtag. And as you can remember, this response should contain an open redirect. Now, as the front end is not using the hash, it's just normalizing the path, we can include this path traversal and then the resource that we want to modify. Now, as you see, we get the same response, private, no store, so basically it seems like it didn't work. But if we send a request again, you can see that it was stored. And if we send a request to main.js, which used to have a 200, now it's a redirect. So let me send this attack again because it's going to last for 25 seconds. Okay. So when we load the home page again, we get arbitrary web cache poison. Okay, so basically these are the defenses we can apply to protect against these attacks. The first one is to protect against web cache deception, always use the directive, the cache control header with the private and no store directives. However, as we just saw, this sometimes will not work, so try to see if it's possible to disable this feature that is overriding the cache control header, and if it's not possible, we'll consider changing the CDN. And also, for defending against web cache poisoning, this is really, again, just choosing the right CDN, because if we are going to choose a CDN that is normalizing the key, then remember that this is going to happen and try to see if there's no discrepancies with the HTTP server so that it's not possible to create even a denial of service or even a worse attack. And you can also use the tool I will provide in GitHub that is a burp extension to detect if there's any path confusion that could be used for web cache poisoning or web cache deception. These are all the different links that were used to create this talk, and also at the end you can find the burp extension link, which is a repository in GitHub. Finally, the takeaways of the session. So as I showed, we can use parsing discrepancies in almost any website to exploit web cache poisoning and web cache deception. All these attacks should work right now because they were not fixed, because they were not vulnerabilities. It's really hard to fix these kind of things because just as it happened with HTTP smuggling, we are exploiting discrepancies. So if I tell, I don't know, if I tell any CDN that they are using a delimiter or they are not using a delimiter, they are going to tell me that they are complying with the RFC and the problem is from the origin server, and it's just going to be a problem of blaming each other. Also, we saw that we can apply all these different techniques in many bug bounty programs. I didn't find a lot of vulnerabilities with this, because, or actually I did find, but I didn't look for many vulnerabilities because I didn't have time. So I invite you all to use this tool to find a lot of targets, and probably you will be able to find a lot of vulnerabilities because last time I checked, there were about probably 10,000 of sites that were using special delimiters. So this is going to be really useful for those that are doing bug bounties. And finally, I showed how we can change these different techniques in order to increase severity. So always consider using
these kind of chains to create new exploits that are going to prove that this should be stored, that this should be fixed in every site. When I first reported this to many websites, they told me that this wasn't a vulnerability, even though I was able to show that the attacker could cause denial of service. So I had to create this new attack to show that we could create an attack that takes control of the entire site. OK, thank you. And I still have some time for questions, fortunately. Thank you.
I have a question for you over here on this side. So for an organization trying to protect their servers, I suppose this is very difficult to detect pre-production, right? So if you're in QA or a developer, I suppose for a pen test team, this has to be in production to have the web cache in the way, right?
Yeah. Usually, it's not easy to detect this because it's not related with the application itself. It's related with the way we configure the web cache and the way we configure our own HTTP server.
Okay. Thank you.